Hey everybody. Today we're talking about hypergeometric distributions. These model sampling without replacement much in the same way as binomial distributions model sampling with replacement. They come up from time to time in statistical inference, for instance in Fisher's exact test for the independence of two categorical variables. Let's jump right in with an example. A bowl of Halloween candy consists of 18 Snickers bars and 7 Butterfingers. A kid grabs 5 at random, obviously without replacement. What's the probability that they get exactly 3 Butterfingers? So we're going to compute this probability directly. First, we're going to count the number of ways the kid can get exactly 3 Butterfingers, and therefore exactly 2 Snickers. So let's look at the Snickers bars first. How many ways can they get 2 of the 18? 18 choose 2. Similarly, there are 7 choose 3 ways of getting 3 of the 7 Butterfingers. These selections are independent, so we can multiply those counts. Overall, there are 5,355 ways that the kid can get exactly 3 Butterfingers. Next, we have to get the total number of selections that could happen, the number of ways of picking 5 candy bars at random from a bowl that includes 25 candy bars. So of course that's 25 choose 5, or 53,130. Now the probability of getting exactly 3 Butterfingers is just going to be the quotient. The number of equally likely outcomes in this event divided by the total number of equally likely outcomes. In this case, it's about 10%. Keep that example in mind as we generalize. Suppose we draw a sample of size n from a collection with n1 objects of one sort, say black chips, and n2 objects of another, say red chips. Then the probability of drawing exactly k black chips is given by n1 choose k times n2 choose n minus k, divided by n1 plus n2 choose n. Let's unpack this a tiny bit. The denominator here is just the total number of ways that n objects can be drawn from the collection, because there's n1 plus n2 total objects in the collection. The numerator is the number of ways that you can select k of the first kind of objects, and then the rest, n minus k, of the second kind of object. The hypergeometric distribution with parameters n1, n2, and n is the discrete probability distribution consisting of all the possible outcomes between 0 and n1 and their corresponding probabilities. Let's work through a full example. A statistics class consists of 16 women and 12 men. A team of 8 is selected at random. What's the probability that only 3 of the people on that team are women? That 4 are? Then let's construct a probability histogram for the number of women on the team. So here we have a hypergeometric distribution. We're selecting people at random for this team. We're doing it without replacement. We're interested in the number of women on the team, in particular, the probability that we get exactly 3. So here, n1 is 16, the total number of women in the population. n2 is 12, the total number of non-women in the population. And the sample size, n, is 8. Plugging those into our formula, the probability that we get exactly 3 women is 16 choose 3 times 12 choose 5 divided by 28 choose 8, about 14.3%. We do the probability that we get 4 women in exactly the same way. 16 choose 4 times 12 choose 4 divided by 28 choose 8, about 29%. We can repeat that for all the different possible values of x, 0 women, 1 woman, 2 women, etc. Either by hand or, I recommend, using R or other technology, and we get this discrete probability distribution. In my next video, by the way, I'll show you how to do this in R. We'll go through hypergeometric calculations in R more thoroughly. If we plot these values into a discrete probability histogram, we get a shape like this. Let's conclude by talking about mean and variance of hypergeometric distributions. As before, let's have the parameters be n1, n2, and little n for the number of objects of the first kind, second kind, and for the sample size that we're taking from that collection. When we write down the formulas for mean and variance, it's going to be helpful to have notation for the total number of objects in the population. So we'll write big N is n1 plus n2. And for the original proportion of black chips in the bag, so n1 divided by n. the proportion of sort of objects of the kind that we're interested in this calculation. Then the expected value for the hypergeometric distribution with these parameters is just n times p. And the variance is n times p times 1 minus p times big N minus little n over big N minus 1. Now, that second one in particular is a little bit complicated, but I think these are both simplified when we remember our mean and variance for the binomial distribution. The mean is np, so that's exactly the same as we have here. The variance is n times p times 1 minus p, so very similar to what we have here. In this case, we just sort of have that correction factor, big N minus n over big N minus 1, to account for the fact that we're doing the sampling without replacement. In general, drawing without replacement has the same expected value, but lower variability than drawing with replacement.